Hi people, Kinematics. So kinematics is all about the study of the motion of objects, and if you've done physics, this will all be very familiar to you, but you should have done it in science last year anyway. So we often talk about cars. This was a car and then it turned into a beetle. However, I'm not here to admire my drawings. It's to study the motion of objects. And when we're doing this in calculus, we're only going to consider motion in a straight line, all right? So we're not going to consider different types of motion like parabolic motion. We're just going to consider straight line motion. And to do that, we're going to consider particles moving backwards and forwards across straight lines, given to relative to a reference point, which we call 0 generally, and we often refer to that as the origin. At any time, we can measure the displacement from the origin. Now remember, there's a difference between displacement and distance, and we'll talk about that in a second. So that is basically the position at any time. All right, that's what your displacement means. It's the position at any time, and we're going to talk about that relative to the origin, how far you are from where you started. Since this is all changing always, all the time, so as you're moving, you're changing your distance, you're changing your velocity, you're changing your acceleration. We describe displacement from the origin as often as a function of time, so we call it S of t. Sometimes it'll be x of t, it'll be h of t, whatever it is, it's always going to be a function of time. Now from science, you know that the average speed is calculated by the distance travelled over the time taken, whereas your average displacement is calculated by the change, and that sign means change, remember, change in position over the change in time. Okay, delta sign means change. So we could write this, if we're writing it in more mathematical terms potentially, we could write it as follows. We can write that as S of T2, take S of T1, all over T2, take T1. In other words, the position at time 2, take the position at time 1, divided by time 2, take time 1. If we're thinking about this, a graph, so this is a position, that's T2, and that's T1 because we've got time there and S there. This would be S of T2, and that would be S of T1. So let's just qualify what the difference is between distance and displacement. So if we've got something that looks like this, an axis, and on that axis we have our 0, our origin, but we've got some other times going on here. We've got 3 and 7, and we've got something happening at -1 and -6. All right, and our distance, or our displacement as well, is modelled by this. It's modelled by this line, which is describing to us where we're going. All right. Now, if we're talking about distance, we would say we'd add up the total distance travelled. So we'd go distance travelled is going to equal that total distance starting from the start, which was there at 3. So we'd go, oh well, we went 3 to 7, so that's going to be 4. And then we went 7 to -6, that's actually 13, because it's 7 back to 0, but then it's another 6 to get back to -6, plus 5, -6 to -1. And so that's going to equal 22 units. The displacement, however, so that's the change in position, and that's equal to -4 units. Now, why that is the case is because you started at -3, at +3, sorry, and you ended at -1. So you ended up to the left of where you started by 4 units. All right, so that's why we've got the -4, because left is negative, and it's 4 units because that's the difference in position between the start and the end. Change in position. It's not change in position from the origin, it's the change in position from the start. All right, so just remember that. So that's a bit of theory behind kinematics. And so the questions are really quite simple. All we are doing is an application of what we've learnt so far. So if we think about the change that could occur between times t and times t plus 8, where h is just a small amount of time, the average velocity is going to be, instead of calling it s of t2 and s of t1 now, we're going to call it s of t plus h, take s of t all over t plus s of t all over t plus h, take t. Alright? That's just the formula for slope. That's just going to give us s of t plus h, take s of t all over h. And this is very similar to what we've done before. If you're talking about average velocity, that's just simply the slope of the chord on a graph of displacement versus time. Which we then can simply calculate it using the formula that we just talked about, that formula above. So if we, though, allow the time interval to become smaller and smaller, all right, so h is becoming smaller, basically, we approach the quantity known as the instantaneous velocity. So this is known as the instantaneous velocity, and that is the velocity at any moment in time. And we call that v of t. Now I'm just going to draw a graph because that's been a lot of talking without much pictorial representation. You're probably going, what is going on? So if we've got s of t over here and we're graphing that against time, and we've got a graph that looks like that. All right? This is our origin down here. This is t, and this is t plus h. This is s of t plus h. And this is s of t. Now we just use the velocity formula without thinking about this graph to go, well, this is the definition of velocity. It's the change in displacement over the change in time. But then if we compare that to a graph, the change in displacement over the change in time, well, that's the slope of that chord, isn't it? It's the slope of the chord joining the 2 points. Then if we think about h becoming smaller and smaller, of course, that's going to give you the tangent slope. Okay? H is becoming 0. So as the time interval becomes smaller and smaller, h approaches 0. Therefore, the instantaneous velocity is actually the limit as h approaches 0 of s of t plus h take s of t all over h. Now that should look familiar because that is simply the limit formula. So that simply tells us that to find the velocity, moral of the story, all we have to do is find s dash of t. Now, if we do exactly the same thing with the acceleration, we eventually get that acceleration is v dash of t. So it's the derivative of the velocity function, or it's what we call the second derivative of the displacement function. So you just find the derivative first to find the velocity of this, and then you find the derivative again. Now I'm going to copy out the explanation of why that is, but if you don't really need to know, as long as you know that to find the acceleration you just need to differentiate the velocity. But if you want to copy that in, you can. So each time we differentiate this displacement function that we had up the top here, each time we differentiate this thing up the top, we get a rate per unit time calculated. So if we're then putting units, which we have to put units, we'd get the units of velocity, which are meters per second, or you could write it like this, meters per second. And then we get the unit of acceleration, which is meters per second, or meters per second squared, or meters per second to the -2, whichever one you're feeling like. So I've just copied the explanation for why the acceleration is the way it is, if you're interested. Now we'll do some examples, because this one involves more differentiation. So a particle is moving in a straight line, so that its position, x meters, at any time t seconds is given by this function here. All right? So you've been told to find the average velocity. Well, this is finding the average velocity. This is not telling you the instantaneous velocity. So what you're going to do is use the formula for velocity average, which is simply going to be t2 take t1. So the position at time 4 take the position at time 0 all over that difference in time, which is 4 take 0. So basically changing position over changing time. You don't have to differentiate here. So to do that, you need to know what x of 4 is, and you could do that on your calculator simply by plotting it, or you can just work it out. So that's going to be 4 cubed take 6 times 4 squared, just substituting that into there. And you get negative 32. And so then you just do also x of 0. So x of 0 is just going to equal 0 cubed take 6 by 0 squared, which is just equal to 0. So you're going to get negative 32 take 0 on 4, which is negative 8 meters per second to the negative 1. I have not done any differentiating there. I'm simply using the formula for average velocity. Okay? Changing position over changing time. But then I get asked to find the velocity of the particle when t equals 2 seconds. So what I'm being asked there is to find the derivative, find the change in the position. All right, find the instantaneous velocity. That means I have to find the derivative. Okay, so remember v of t is equal to the derivative of the position function. Now you might be going, well, it's not s. Remember, you can represent it any way you like, and we've been told up here it's x of t, so it means it's x dash of t. So let's differentiate that function. We'll multiply down, subtract 1, we'll get 3t squared take 12t. So if we're trying to find it though when it's equal to, at t equals 2 seconds, we'd do v of 2, which equals 3 times 2 squared take 12 times 2, which equals 12 take 24, which is negative 12 meters per second to the negative 1. All right? Easy. Then it goes, determine the time intervals for when the particle's velocity is positive or negative. If it's asked a question like this and it's asking about a sign, probably a very good indication that you should probably draw a sign diagram. Remember, when we're trying to work out positive or negative, that's talking about sign. All right? So sign diagram, sign diagram. To do that though, remember with a sign diagram, you have to find when the function equals 0. Equals 0 when? So to do that, we've got to go, well, 3t squared take 12t is equal to 0 when? Well, let's factorize. 3t outside of t take 4 equals 0. And so we get that either t equals 0 or t equals 4. So that's our critical values. Time can be keep on going. We don't get told a limit on time, but it can't be negative. So if we're doing a sign diagram of v of t, that is going to be the same as, that's why we put this line here and these arrowy things along there. Just draw that a bit nicer with a bit of a finer pen. But we'll draw that, and then we just put these things here to go. It can't go any smaller than that, but it can go on forever. So that's 0 and that's 4. All right, and so let's just try a time in there. So I'm just going to do this from my head. I'm going to do 1. So when t is 1, this function up here, when t is 1, this function up here will be 3 take 12, which is negative. So that's negative. Now we know it's a quadratic function. That means it changes sign. It can't be a stationary point of inflection. So we know that's the other side of it has got to be positive, all right? So we're going negative to positive. Now, does it look like that? No, negative slope, negative to positive, all right? We don't get asked about that, but it doesn't hurt to remember that. All right, so if we're answering the question now, though, remember it's really important to answer the question. So you just write below, I have run out of room, so I'm just going to put it over here. The velocity is positive when t is greater than 0, and it would be good to write it in actual words, not just write the signs, and negative when, now be careful, don't say when t t is greater than, when t is less than 4, because it's not, it can't be less than 0. And when t is 0, it's going to actually equal 0, the velocity. So it's not going to be negative there either. So just be careful there. Then find the acceleration function and hence determine a of 3. So acceleration, remember we said before, acceleration is just the derivative of the velocity. That's going to equal 6t take 12. If we multiply down, subtract 1 with this function up here, we're differentiating the velocity. All right. And so a of 3 then is going to equal 6 times 3 take 12, which equals 6 meters per second to the negative 2. All right, hopefully. Okay, so let's have a bit of a chat about what the different signs of these functions actually mean. So if we've got s of t, remember that when we substitute, that's going to give us the position. All right, it's going to give us the position of an object at any time. If we've got v of t, that gives you the velocity at any time. And of course, if you've got a of t, that gives you the acceleration at any time. Now, when we've got a positive for s of t, let's think about the different signs. We could either have positive, 0, or negative. So if we've got s of t and it's positive, that means that the particle is on the right-hand side of the origin. All right, so the particle we're talking about is right of the origin. And it's of the right of the origin, remember. If we have a positive velocity, that means that the particle is actually moving to the right. And that's because, of course, we remember that the velocity is the displacement over the time. So that means that your displacement or your change is positive. Your change is positive, so you must be moving to the right. Acceleration positive, it means that the particle's velocity is increasing. So the velocity is increasing. All right, so that all suddenly filled out. But if we've got 0 for the s of t, the position, that means that the particle's at the origin. If it's 0 and the velocity is 0 in this case, that means that the particle is actually stationary. That makes sense. Velocity is 0, it's not moving, it's stationary. If the acceleration is 0, remember you can be traveling and your acceleration be constant. Your acceleration be 0. It doesn't mean you're not moving. So that just means that you're moving at the same speed or velocity. You're moving at the same velocity. Now, if the sign is negative, that means that the particle is to the left of the origin. If you've just got the position graph of s of t, if you've got v of t and that's negative, that means your particle is moving to the left. So remember, when it was positive, it's moving to the right. When it's negative, it's moving to the left. If you've got a negative acceleration, that means that your particle's velocity is actually decreasing. All right. Now you might think, why is this even important? Well, you're going to get questions like, when is the velocity increasing? Don't think that's when the velocity is positive. It's actually when the acceleration is positive. So you have to be able to determine when that is. So these are some really important points to have when you're doing questions, that speed is different to velocity. It's not the same thing. For the speed, the direction is not important. That's for displacement is when the direction is important. For the speed, the direction is definitely not important. So speed increases only when v of t and a of t have the same sign. All right? Because if your velocity is positive, remember that just means it's to the right. It's not talking about your speed. And it's only if the acceleration is positive, or equally that the acceleration is negative, that you're going to have a speed decreasing. Now you might be going, well, how can you have speed being decreasing if your acceleration is negative? Acceleration being negative simply means that you are accelerating, but you're accelerating in the opposite direction. All right, so it doesn't mean you're going slower. It means you're accelerating in the opposite direction, and so you can still accelerate. You can still have an increased speed even though you've got negative acceleration. So that means that speed can increase when either v of t are both positive or they're both negative. When they actually have opposite signs, the speed decreases, right? So speed is decreasing when v of t and a of t have opposite signs. And that makes sense. So if that's puzzling your brain a bit, remember, think about displacement and that diagram where we had this going on here, okay? So for example, say you took this though and we talked about velocity, and we said, well, our velocity between here and here is positive, yeah? Because we're talking about change of position, our velocity is positive, but then say you took the velocity right at this point and it's actually less, say the velocity at this point is a and this is less than a, then your acceleration is going to be negative because that's a change in velocity. And so that means that you're actually decreasing in your speed. But if you had a situation more like this, you started here and you ended up here, your velocity here would be negative, all right? But you might be traveling at, and your acceleration would also be negative because it'd be less than over here. But you might be traveling at a really fast speed, but just traveling that way. Okay, so you might be traveling at a fast speed, you might be accelerating, but you're going in that direction, so that's why it goes left. Okay, so think about it all the time, it's to do with the direction, not so much as the actual speed. We can talk about this more if you want to. So if S of t and v, because they're all functions of time, S of t, v of t, and a of t, you can just find the initial conditions using S of 0, v of 0, and a of 0. Now, in all problems, time cannot be negative. That makes sense. It's like with distance problem, radius can't be negative. T is always greater than or equal to 0. Let's finish off with an example. A particle is moving in a straight line with a displacement function S of t equals 2t squared, take 12t plus 1 centimeters. T is greater than or equal to 0. Find the velocity function. Well, velocity is simply the derivative of S of t, and that's going to be multiplied down. Subtract 1 for each of those terms and give you 6t squared, take 12 centimeters to the negative 1. Really important that you always write your units, centimeters per second, Now if we take the derivative of the velocity function, we get the acceleration function, because the acceleration is simply equal to the derivative of the velocity, which is going to be multiplied down, subtract 1, 12t. 12t centimeters squared to the negative 2. Then it says to find the initial conditions and interpret their meaning. Well, the initial conditions are simply when t equals 0. S of 0 is going to be, let's substitute it in. And think about it, if you substitute 0 into this, all you're going to be left with is 1. So S of 0 is going to be 1 centimeter. Then V of 0 is you substitute in 0 into this one, and you would get 6 times 0, take 12, so you get negative 12 centimeters seconds to the negative 1. And then A of 0 is going to equal substituting 0 into this one. So that's going to be 12 times 0, which equals 0 centimeters per second to the negative 2. Now it says to interpret their meaning. All right, let's think about this really carefully. When t equals 0, the particle is, well, let's talk about S of t first. It's 1 centimeter to the right, isn't it? Positive means it's right. Now, velocity is negative, so that means it's moving to the left. And the acceleration is 0. So that means that the velocity is constant. Okay? If the acceleration is 0, that means that the change in velocity is 0, which means that the velocity is constant. Doesn't mean that it's not moving, it means it's constant. So let's write that out. So copy that down. Notice that we've used every bit of information. We've talked about what it means that t equals 0. We've talked about what it means that S of S of 0. We've actually said what it means. We've said what V of 0 means. We've said what A of 0 means. So you've got to make sure that you interpret it actually what it's talking about, left or right, increasing or decreasing, constant, position, etc. Then we're going to draw a sign diagram for V of t and A of t next. Well, of course, when we draw a sign diagram, we have to make it equal to 0. So let's first do V of t. V of t equals 6t squared take 12. Which when we factorize, it's going to give us 6 outside of t squared take 2. Now we can break that up then. This is actually difference of two squares if we write it like this. 6 plus root 2 outside of t take root 2. Alright, because if you expanded that through, you've got difference of two squares. You'll get t squared take root 2 squared, which is really t squared take 2. Your acceleration, we've found that before, equals 12t. So now if we do our sign diagrams of that, we know therefore that there's this V of t is going to equal 0 when t equals root 2 or t equals negative root 2. Now of course t can't equal negative root 2. Same with S of d, 12t is going to equal 0 when t equals 0. So that's our only critical value there. So if we draw sign diagrams, they will look something like this. So initially, let's do V of t. So the sign diagram of V of t is as follows. We again remember that t is not allowed to be less than 0, so we put those lines there. And then we draw our sign diagram and we put on our critical point, and we've only got one, which is root 2, because negative root 2 can't exist because time can't be negative. Then again, we'd sub in a point that's between 0 and root 2, and so something like 1 is fine. If you substituted 1 into V of t, you'd get 6 take 12, which is a negative number, so that's going to be negative and that's going to be positive. That's our sign diagram. If we're doing a sign diagram of A of t, we're just going to have only one critical point. That's the critical point at 0. It's going to continue on like that forever. You substitute any point into here that's bigger than 0, you're going to get a positive value. So that's the sign diagram of A of t. Now, this is where our little table that we did before is really helpful. We go, at what time is the particle's speed increasing? All right. So remember that the speed is increasing when we have the same sign. So let's look at this. When do we have the same sign of A of t and V of t? Well, if we look at this and we've sort of put them on top of each other, that's only going to occur in this section, isn't it? Because down here, when t is less than root t, it's going to be negative. So the speed is therefore going to be increasing when t is greater than root 2. When is the velocity increasing? Really important thing, velocity only increases when the acceleration is greater than 0. Okay? When the acceleration is positive, the velocity is increasing. So that's when we have to look at A of t only. And the velocity is increasing for all t greater than 0 because A is always positive. So that's where you just have to be really careful and go back and look at that initial diagram that we had with all those boxes of S of t and V of t and A of t. Velocity is only increasing when the acceleration is greater than